Tangents today. You guys know them as opposite over adjacent, but there's a new version of tangent out there. Here's what a tangent is. You guys can read it, but take a look at my diagram. All three of these lines are tangents. Take a look at the second diagram. None of these are tangents. See the difference between the two? Describe to what a tangent is. Go ahead, Nick.
It's like a ray with one point touching the outside of the circle.
Okay, I'm even going to go further than a ray. A line. Make sure you guys realize it's a line, all right? A line that intersects a circle, one spot. Quick question. This intersects the circle at one spot. At you. Why isn't this a tangent? Well, it's a radius, and also is it a line? No. This one touches it at one spot at W, but why isn't it a tangent? It's a ray, it's not a line. If I did extend the line, what would happen? Twice. Okay, it'd be twice. So it has to intersect the circle at exactly one spot. Okay, and yes, it'll always be on the outside of your circle. Okay, on the outside. We okay on a tangent? Intersects the circle, one spot, and it's got to be a line. Okay, let's talk about common tangents. Two circles, one line that intersects both of them in one spot. So take a look at my first one here. I'm predicting that these circles have two common tangents, meaning I'll draw one so you know what I'm talking about. I can draw a line, one line that intersects each circle in exactly one spot. Here's one of them right here. Everyone see how that one line intersects both of them at one spot? But I'm saying there's two of them. You know where the other, can you find the other one or draw the other one in? And hopefully most of you are drawing it down here. There you go. Okay, so a line intersects the circle exactly one spot. All right, the next diagram, now that they're not intersecting, I pulled them apart. I'm saying there's four tangents. Can you find them? Four common tangents. Can you find it? Excuse me, a single line that intersects both circles in exactly one spot. Can you find all four common tangents? We're drawing in a line. Intersects both circles exactly one spot. Good, good. Getting one right diagonally with a positive slope, getting one diagonally with a negative slope, and then these two right here and here. There they are. Next one, I'm making no predictions. Do you think you could find how many common tangents there are when they're just touching? Two circles that are just touching. How many common tangents do you think you have? Well, I know, I'm sure people put one here on the top, just like we did above, and put one on the bottom, just like we did above. Anybody have another one, or is just those two? Sean? Yeah, because these are just touching in one spot. So once you draw that one in, you're hitting it each circle in one spot. So they have three common tangents. Yep, three common tangents. And what about if it's a circle inside the circle, just touching? How many common tangents can I draw now? Can you, is it possible? Where is it possible? Yep, the line goes through their point of intersection. Yep, so just one common tangent here. Oh, hold on, I got a quick question. I got one common tangent. I got two, I got three, I got four. Is it possible to have none? Two circles, you can draw two circles that have no common tangents. Is it possible? Anybody remember what we called those circles? Where they shared the same center? It's our concentric. Your bullseye, your dartboard. Yep, right there. Those two circles have no common tangents. Yep. So it looks like we're pretty good on the common tangents then. All right, facts now. Facts. Can you guys, you got some room? Yeah, you got some room somewhere there. You got some room. Draw yourself a circle with a tangent, please. Draw yourself a circle with a tangent somewhere here. Okay, let's stop calling it the point where it intersects the circle now. Okay, let's stop calling this the point where it intersects the circle. We're going to call it, these mathematicians are pretty clever. We're going to call it the point of tangency. Okay, the point of tangency. That's where the tangent intersects your circle. The point of tangency. Okay. All right, here's your first circle theorem for tangents. Everyone make a center point. Make a center point, please, on your circle. Draw in the radius to the point of tangency. Draw a radius into the point of tangency. Here's your first tangent theorem. If you have a radius drawn to the point of tangency, it is perpendicular, yes. Okay, so if the radius is drawn to the point of tangency, it's perpendicular to the tangent. Every time. It's got to be a radius, though. Radius or diameter, I guess, but it's got to come from the center. It's always perpendicular to the point of tangency. Any questions here? All right, calculators need one. We all set? Let's get one because we're going to crunch some numbers here algebraically. Ready to go? So for this first one, everyone see a tangent line. Everyone see a radius drawn to the point of tangency. What's happening? What's being created? It's perpendicular. A right angle is being created right here. So I am allowed to put a right angle symbol in here. Radius drawn to the point of tangency is perpendicular. And now how can I find angle x? I can do, yep, 180 minus that right angle, minus the 58 I was given. That'll let me know x will be 32. 32? Degrees. So now that you know, you'll be seeing some right angles formed. What else can we do in right triangles? Oh, Pythagorean Theorem. Funny you bring that up. Here we go. Find the value of x now. And in every diagram, AB is tangent to circle C. You guys see where the right angle would be in this diagram? Where's the right angle going to be? Name the angle that's a right angle. B, yep. Okay, so you have a right triangle, a little Pythag. All right, name a leg. Here you go, name a leg. 8 squared plus other leg, x squared. Watch your mouth here. How about the hypotenuse? Yep, I'm going to write x plus 2, but x plus 2 squared. So I'm going to need your help here. 64 plus x squared. How's your algebra skills here? What am I doing to the x plus 2 squared? It's not x squared plus 4. Sorry, guys. Not x squared plus 4. What am I doing with this? Yeah, yep. What am I doing with this? X plus 2 times itself. Yep, and we're doing a little double distribution. So I'll let you go. I'll ask somebody in a second. Okay, x squared, what do you have as a middle term? 4x. And then your c value? Plus 4, yep. What the heck you want to do with that? Get everything to one side? Well, what's going to happen when I subtract the x squareds? Everyone see the x squareds are gone? Whether you move this one over to the left or this one over to the right, x squareds are gone, so you're left with 64 equals 4x plus 4. I'm hoping now you can solve that. Get the x by itself. I'll ask somebody here, or just the group, because it's worthless calling on numbers because no one's here. You get x equals 15, yep. Questions, comments? All right, let's roll. Right angles at B again. Again, radius, draw no point of tangency, perpendicular. But I didn't give you all the sides this time. I didn't give you all the sides. I know one of the legs is x, so I'll go x squared. What about this other leg here? Or can I even use Pythag? Why is it 3, Kate? It's the radius, right? All the radii in a circle are congruent. Nice. So that'll be 3 squared. And then my hypotenuse here? 10 squared, yep. Can you just leave it in radical form here? There's no reason to go decimals. X squared equals, what are you guys getting, 91. And I'll just save you some time. You can't break down the square root of 91. There's no perfect square that goes into it, so we'll just leave it square root of 91. Okay, before you guys get going with 4, I'm going to save you a lot of frustration. I know it's a right triangle because this is perpendicular, so it forms a right angle. One leg is 12 squared. What about the other leg, CB? Why? It's a radius. You learned your lesson from the last one, right? Now, most of you, for the hypotenuse, is probably going to put x plus 9 squared and do all that, right? Which is fine if you want to. That's fine. I think some of you prefer not to do any foiling or double distributing if you don't have to. How about we just do this? How about we just find the length of the entire hypotenuse? Find this entire length by doing c squared. And then what could I do at the end to find x? Take my hypotenuse and subtract 9. Okay, I think it's a little easier than trying to because I would let you know at the end here you'd have to factor. I don't know if anybody wants to really factor right now. Probably not. Is that 225? So what is that entire hypotenuse in the diagram, CA? 15? So finding x will be 15 minus the 9, so it's just going to be 6, yep. Okay, here's where you're going to have to do some work on your own. A quick proof here. That's going to lead us to our last theorem of the day. I need your help proving BA is congruent to BC. Only way we're going to do that is how? Prove the triangles so we can say CP, CTC. So whether you want to move around and work with other people or work by yourself, try to find as many congruent pieces in both triangles as you can, knowing what you know about circles. And I'm telling you, BA and BC are tangent to each other. Okay? Try to find as many congruent pieces as you can. Maybe, hey, if you could get the triangles congruent, that'd be awesome, but I'll help you out with it. Try to get as many congruent parts as you can right now. Try to get as many congruent parts as you can. I'll give you about 2.5 minutes. Even if you know it's true, write it down, and if you don't know the reason, that's fine. Leave it blank. So, all right, fill me in here. What parts did you get congruent? What'd you label on your diagram? Mike, what's one thing you labeled? Okay, angles A and C are right angles. Everybody stop right here. I can't put the right angles yet. The theorem doesn't say right angles are formed. What's the theorem say? The radius and the tangent are perpendicular. That's what I'm going to use that theorem for now, is to say that OA is perpendicular to AB and OC is perpendicular to CB. And here's the theorem in a nutshell. I have a radius drawn to, where's it drawn to? What do we call that point? Yep, a radius drawn to a point of tangency. Nope. We do enough abbreviations in here. A radius drawn to a point of tangency is what? Perpendicular to the tangent. Okay? This is not saying that you right angles are formed. But now that you have the perpendicular lines, now you could say angle A and angle C are right angles. And that's an old reason, which is perpendicular lines form right angles. All right, thanks. Good job, guys. That's true. Any other things you want me to put up here that maybe you marked on your diagram, or you want me to go further here? Max, what do you got? Okay, angle A and angle C are congruent. I'll write that down. All right angles are congruent. Got it? Did you guys find anything else other than the right angles? Hugh? Yep. OA is congruent to OC. This is a reason we've used when we did the proofs a couple days ago, which is, yep, got to have the inner circle part. In a circle, all radii are congruent. All right, let me mark those radii. Got it, got it, got it. Anything else in that diagram I can throw up there? The reflexive side, yep, always can rely on that, right? OB congruent to itself. Boy, I got a Max. Where I was just going to say this. We're talking on two different pages right now. Correct. You cannot say side-side angle, but they are congruent. By? Everyone remember hypotenuse leg in a right triangle? Hypotenuse, OB, and leg. Yeah, everyone forgets about good old HL. But before I use HL, anybody remember back in the day? Because it's not ready for HL yet. Justin? You need to say the right triangles before you use HL, yes. So triangle, what do we have? AOB, or however you want to say it. AOB and triangle COB are right triangles. Anybody reason? Right triangles have right angles. Then you can bust out the old HL to say they're congruent. Triangle AOB congruent to triangle COB. HL, and then the two sides would be congruent by CPCTC. I'll just let you guys, if you ever want to remember this could have been done in one less step. Because I used HL, you don't need to tell me the right angles are congruent, remember. Okay, you do need to tell me they are right angles, but you don't need to tell me they're congruent if you're using HL. All right, why did I have you do this whole long proof? Yes, to go over some circle facts, but also you just proved a theorem. You prove BA being congruent to BC. You do not need to do all this anymore. There's a theorem out there that says every single time they'll be congruent. And I think I need to go back. I guess I didn't copy the text box, but here is the theorem down below. What are those, BA and BC? They're tangents, right? And they're drawn to the same point, B. Everyone agree? They're drawn to the same point. So here's our theorem. Tangents drawn to the same external meaning point outside the circle. Yep, the same external point are congruent. And if you want to just make a quick sketch of what we're talking about, nothing fancy, they will always be congruent to each other. Some people like to call this the party hat theorem. All right. Okay, whatever you want. The party hat theorem. All right. Let's use it now. Let's use it. Find the perimeter of each polygon that's circumscribed. Circumscribed meaning? Anybody circumscribed? The polygon's on the outside. So every one of these figures, all of these triangles, what's the perimeter? And you're going to use that previous theorem right now. You may not see it, but you're going to use it. So perimeter means all sides added up. So far, I have a side of 7. Right? Side of 7. I have no idea what the other sides are. But you can use the theorem we just proved. Ready? I don't know if you see the party hat theorem going on, but right here, let me cover up the rest of the diagram. Everyone see these two tangents right here being drawn to the same external point? They're congruent. This one's 3, so the other tangent going to the same point is 3. So now that's a total side of 8. Now what about this huge missing side here? Can you help me find that side? All right, well, here you go. Again, two tangents being drawn to the same external point are congruent. 4 and 4. And what about this piece here? Everyone see it coming from here? Two tangents drawn to the same point, so that's got to be 5 for a total side of 9. Everyone see how I'm using that theorem right there? And then this perimeter would be, what do we got, 24 centimeters? See if you and your group can apply that theorem to 6. I gave you 2 full sides. So you guys know the perimeter is going to be 8 plus 9 plus something. Anybody want to help me out? Because I know I can't say 6 and 6 because that's not how the theorem works. I can't say 6 and 6. Anybody want to? If that's 6, everyone, this will be 6, right? Okay, go around the triangle now. This will be 3. This will be 3 and so the missing one was 5 for 11. So you get 28 inches out of that. Perfect. All right, let's try to put this all together and wrap it up. Try to find x for 7. Okay, try to find x for 7. Remember the theorems we went over today. Both theorems. See if anybody can pick it up without my assistants. It's not a triangle, so don't tell me it's an isosceles triangle. All right, it's not a triangle. What else are you guys adding in on your own to this diagram? Right angles, right? Tangent, radius. Hey, radius drawn to a point of tangency is perpendicular. So, yep, you have right angles here and here. All right, great. How's that going to help me find x? This is a 1, 2, 3, 4-sided figure, a quadrilateral. How many degrees? 360. There you go. So x equals 360 minus those other 3 angles. And that ends up being 50 degrees. All right. 8 has nothing to do with tangents because there's no tangents drawn, but you can use your circle facts for this unit. Go ahead, try to find x if you haven't done so already. Has nothing to do with tangents, none are drawn. So use your circle facts. Use your circle facts to find angle x. And 50 is pointing to the angle inside the triangle. Thoughts? If I give you that 50, where can I go from here? One main circle fact you're using. We're all in the same circle. Radii are congruent. Yes, they are, meaning this is now what type of triangle? Isosceles. The sides across from the angles across from the congruent sides, both 50. So x turns out to be 80 degrees. Questions? Okay, we got one more tough one here. All right, definitely focus in on this one. ZY's tangent. What are the 12 and the 9? Okay, what's happening then? If ZY is a tangent line and OZ and PY are radii, what's happening? What's being created from today? Put them on your diagram. Go ahead. Where are the right angles on your diagram? At angle Z and angle Y. Okay. Now, many of you maybe would say right away, oh, it's a rectangle. X is 25. I'm done. No. That's not a rectangle unless these two are right angles, which I have no idea. Oh, boy. So how can I find X? Here's what we're going to do. Well, I'm not going to make it into 2 triangles. I'm going to make it into a rectangle and a triangle. Everyone see the shorter rate? Which one's the shorter radii? YP, right? 9. So what I'm going to do is I'm going to draw a line over to the radii of 12. Take a look. I'm going to start here at P. I'm going to make a rectangle out of this top piece here. All right, so I'm going to take P, draw it over to OZ, and everyone see how I made a rectangle and a triangle? A rectangle and a triangle. Everyone see that? Yes, no, maybe? Yep. Here you go. Here are your right angles here and here. Can you fill out any more values now that you know it's a rectangle and a triangle? And this radii was 9 here. Can you guys help me fill out any more values? Okay, so across from here was 9. And the whole thing was 12, so this part will be 3. Can you guys help me fill out one more length? The line I drew in, since it's a rectangle, opposite sides are congruent, is 25. Anybody see how I'm going to find X yet? Not yet? What do you got, Hugh? Pythagorean Theorem. I wasn't saying that you're correct. Look, if that's a right angle, guys, what's right next to it? Another right angle, right? So you have a right triangle, you know two sides, trying to find the third. Nice job, Hugh. How's it going to look? How's this Pythag going to look? 3 squared, what's the other leg? 25 squared equals x squared, yep. Yeah, there's the right angle, right? Hypotenuse is always across from the right angle. Again, all I'm doing is I'm taking the smaller radii and making a rectangle with it. All right, making a rectangle. So we have 9 plus 625. 625. And I won't ask you to break this sucker down, so we'll just go nearest tenth. $25.2, no units, okay. Hey, before we end this today, ask questions because there's another one that's going to appear on your homework over the weekend. Just like this, a pulley one. So you take the shorter radii, make a rectangle out of it and a right triangle. Okay? Yes, Mike? How do you know where to draw that? You're just drawing it to a point on there because you know that if you're drawing a rectangle, if that whatever the length this radius is, it's got to match it directly across. Okay, so it doesn't, could I have drawn it up here, here? Sure. You just want to make a rectangle and a right triangle. Okay? Anybody else? Okay, I'll leave it at that.